All right, let's have a look at question 8 now. Sorry. So this question is saying there is a roller coaster and it's arranged so the normal reaction force on the top of the circular arc at point P is 0. If there's no normal reaction force, then that means that the force due to gravity, mg, is being completely cancelled out by the centripetal force, the force due to spinning around in a circle. It's not being cancelled out by the normal force. Oops, sorry, why don't I write force G there? That should be force C. So because it's spinning in a circle, that force is pushing it away from the circle is equal to the force pushing it back down, which means it experiences 0 force. Now, if we want our centripetal force, we can use our equation from up here, which is F equals mv squared over r. So that's what we're going to use for this one, F equals mv squared over r. And we also know mg. So that what we're saying here is mg equals fc. And we're going to cross that out and we're going to write that as mg equals mv squared on r. And we are looking for the velocity, so we'll do some cancelling and some rearranging. And we're going to get gr equals v squared, so we'll go square root of gr equals v, which means square root of 9.8 times by the radius, which is 6.4, equals our velocity. And our velocity will therefore equal 7.9 meters per second. Cool. All right. So the whole idea of this one is you're working out that anytime something's spinning, there's going to be a force pushing it away from the center of the circle, which is our centripetal force, which we can get using this. And there's also the force of gravity. If these are cancelled out, then we've got 0 net force. It also, you get this 0 gravity things where a plane's flying in an arc like this. Same sort of scenario. You want the centripetal force to be balanced out with the force due to gravity. All right. This one's a pretty tricky one. It's answered pretty badly on the exam, so I thought I'd keep it in here anyway. It's not technically, it's a circular motion one. Here we've got a faulty car. It only reaches 4 meters per second at the top of the arc at point P. Calculate how fast this car will be moving when it reaches the bottom at point Q. The tricky part about this is we are not given the mass. So what we want to do here is we want to compare the kinetic energy and potential energy at the start. So we're going to have, at the start here, right, he's traveling at 4 meters per second, so there's a certain amount of Ke, and there's a certain amount of potential energy. And once he gets down here, there's no more potential energy because the height's lost and it's all Ke, or kinetic energy. So we can write that out as Ke plus Pe equals Ke after. And I'm going to put in my equations here, and I'll write that as a half mv squared plus mgh. And I must admit, when I first looked at this, I wasn't really sure how this one would work out. But if you're not given mass, and you've got something like this, it's definitely worth writing your equations in because it might come to you in the end. A half, I might actually swap this to, we'll call this the initial speed, mu squared. And we'll call this mv squared, just so we can tell the difference. All right, so then we can now see that we've got mass on one side, mass on the other side. So if I divide all this side by m, that means I'm cancelling those ones out. So there goes my mass. Happy days. So I can rewrite this out as a half u squared plus gh equals a half v squared. Do another bit, we'll times the half onto the other side by times by 2, and I'm going to get u squared plus 2gh equals v squared. And now I'll just square root all this, and that'll leave me with v. Plug that in, and you should end up with 10.7 meters per second. Really tricky because it's not giving you m. I imagine if you got this step here, or you'd probably be getting some marks at this point. And then hopefully once you put in your variables, you can work it out from there.